Good afternoon, everyone. I'm David Hahn, the Craig M. Burge Dean of the College, and I would like to welcome everyone to our third installment of our new spring faculty lecture series. Our goal remains the same: to share our research success and impact with our alumni and friends, many of you who generously support this college and have truly helped make this happen. Today's talk is entitled Keeping Space and Planets Safe. Now, Star Trek famously opened each episode with the voiceover narrative, Space, the Final Frontier. And I think just as Arizona was once a key part of the Western frontier, hearkening images of the Wild West, space is indeed the final frontier, and elements of the Wild West do ring true. My colleagues will tell you a great deal about objects in near-Earth space, but I will start with a simple number. The U.S. Space Surveillance Network tracks nearly 20,000 artificial objects in orbit above Earth. As you will hear, these are just the objects large enough to be tracked and counted. That's not to mention natural objects such as asteroids and comets. So avoiding chaos above the Earth and protecting trillions of dollars of assets that ensure the reliability of our navigation and commerce requires new technologies and new ideas. The University of Arizona has a history of excellence related to space, from world-class observations to groundbreaking space missions such as OSIRIS-REx. Today, you will hear about how University of Arizona observational tools and artificial intelligence algorithms are helping scientists untangle this congestion in space. So I'd like to introduce our panelists. I'll start with Dr. Roberto Furfaro. Roberto is currently a full professor in the Department of Systems and Industrial Engineering and holds an additional appointment in the Department of Aerospace and Mechanical Engineering in the University of Arizona. He serves as the director of the Space Situational Awareness Arizona initiative and currently is the PI of the Air Force Research Laboratory Cooperative Agreement around space situational awareness. He received his PhD in 2004 from the University of Arizona in aerospace engineering and his MS in aeronautical engineering from the University of Rome. From 2010 to 2016, he was the systems engineering lead for the Science Processing and Operations Center of the NASA OSIRIS-REx asteroid sample return mission. He is currently the lead for the target follow-up team of the recently selected NASA Near-Earth Observer NEO surveyor mission. For his contributions to space missions, the asteroid 2003 WX3 was renamed 133474 Roberto Furfaro, which is wonderful. I'm pleased to also announce that Roberto was recently named as the College of Engineering 2021 Da Vinci Fellow in recognition of his research excellence. And I'm certainly grateful to many of you in the audience, our Da Vinci Circle donors who really helped to make that happen. Roberto, welcome.
Thank you very much. It's really a great pleasure to talk to this audience.
Excellent. I'd like to introduce our second panelist, Dr. Vishnu Reddy. Right now, Vishnu, unfortunately, is in an AFRL meeting that they called at rather short notice. So he is going to join us probably in about 15 minutes for the Q&A. But I would like to go ahead and introduce Dr. Reddy now. Vishnu is currently an associate professor in University of Arizona's Lunar and Planetary Laboratory, having joined in 2016. Vishnu received his PhD in Earth System Science and Policy from the University of North Dakota in 2005, also earning an MS in Space Studies. He earned his BS in Visual Communications from Biosphere University in 1998 in Tamil Nadu, India. Dr. Reddy's research focuses on understanding the behavior of space objects, both natural and artificial, using a range of Earth and space-based assets. His work on natural moving objects is directed towards their characterization for impact hazard assessment and mitigation and resource utilization. Prior to joining LPL, he worked as a research scientist at the Planetary Science Institute. He received the NASA Carl Sagan Early Career Fellowship and has received numerous NASA Group Achievement Awards for his work on the Dawn spacecraft science operations team. So again, we'll welcome Vishnu in a moment. Roberto, before we get into your technical presentation to kick this off, let me talk a little bit about our educational mission and how might educational institutions such as ours keep pace and prepare our students for work in space, be it space missions or observations beyond their university days.
I think, yeah, thank you for the questions. It's a good starting to talk about this. I think U of A in general and the College of Engineering in particular are very unique. We all know we're a top research university, you know, but we don't do just far front basic research. We go beyond that. We know that university builds, operates, conducts space mission, instruments. Now we're moving toward CubeSats. Just this is to mention a few. We started also developing the hypersonic program, which I'm also interested in part of this, and work with national labs on a variety of defense programs. So here students do not have just the opportunity to write a thesis or write a paper. They also have the ability, there are opportunities for hands-on experience. Just to give you an idea, as my role as a system lead at the, what we call SPOC, the Osiris Rec Center, I hired basically 10 graduate students. In all, they were splitting, you know, duty, just working on Osiris Rex mission, as well as getting masters and PhDs. And I have to mention that, you know, 3 of them actually got hired after graduation to stay on the mission. Other 2 of them got hired by Kinetics, who's the one that basically drive the spacecraft. And one of my PhD students, probably, you know, one of the brightest that I had, is actually maneuvering, as a matter of fact, Osiris Rex. Wow. And, you know, I have 2 other students here, Enrico and Andrea, who are both working on the NASA NEO surveillance mission. So, I mean, this is a huge opportunity for students to get involved. I don't believe that other universities, very few universities have this kind of opportunities. Yes. And that makes it's a huge discriminant for us.
It is great, absolutely. You know, the hand-in-hand nature of research and education is certainly an example of what you do. So thank you for that, and thank you for, you know, mentoring our students. So I'm going to turn this over to you to make your, you know, formal presentation. You can share your screen, and when we're done, we'll move into our Q&A. So Roberto, the floor is yours.
Thank you very much. So let me share the screen, as a matter of fact. So the overall team is keeping space and planet safe, but the subtitle I would put here is Space Domain Awareness and Planetary Defense, which are the 2 pillars that are needed to ensure this overarching goal. And I want to talk a little bit about some collaborative efforts happening at the University of Arizona, more specifically tie between College of Engineering and College of Science, especially Lunar and Planetary Lab. And this is, you know, something that both, you know, Vishnu and myself prepared, although I'll be the one talking, and Vishnu will join later on about this. Okay, so we are in a space renaissance era, you know, for the space age. More and more satellites are putting up in space. You know, we're talking about many companies putting small sat or CubeSat type of constellations. And one thing that you see, for example, on the top right panel here is a streak of dots, you know, that actually this video was taken in Nevada, and this is not coming from a telescope, it's just you can see it naked eye. And what is this? This is a string of a Starlink, of a set of the Starlink, portion of the Starlink's small sat that SpaceX started putting in space about a year ago. So Elon Musk wants to put a constellation of about 12,000 small sat, order of 250 kilos, in space to provide global coverage for internet. The bottom here, right, what you see another impressive, you know, video which represents basically the you know, the deployment of something like 100 CubeSats. You know, those are 3U 30, you know, 30 centimeters, deployed from the from one of the India launchers, you know, that was able. So you see how much stuff is being just deployed in space just at once. Okay. All right. So it's moving forward. Another thing, and then of course this raised the problem. How do you track these? The discipline that deals with this is called space domain awareness. This historically was called Space Situational Awareness, but recently they changed the name. So from space situational awareness to space domain awareness. And I like to report one of the phrases that I always hear when we deal with the Air Force now with the Space Force. Space is congested and contested. And the reason is because, David mentioned the 20,000 racing space objects in space, but this number keeps growing and growing. The last number that I heard was 29,000. And those are all objects larger than 10 centimeters in diameters, right? We estimate something like 500,000 objects less than 1 centimeter in space. And of course, the problem is that, there is an NRC report where they say we're tipping point, because when this object collides, it creates more debris, and then you have a cascade effect, which is known as a Kessler syndrome, where this population of debris explodes. So you will hear more and more. This number keep updating here. Just to give you an idea about the growth of this is, this is the number of objects that have been, tracked, the inert objects. And the interesting part is as a function of time. It's already outdated. It's 2 years older. But you see that there is a spike here in 2008, 2007, 2008. And this spike is due, these two spikes basically are due to a collision between two satellites, the Cosmo Sky satellites, Russian satellites with an Intelsat, generated a humongous amount of debris, but also another spike due to the fact that the Chinese, as a demonstration, government actually shoot one of his own satellites, and this created quite a bit of population. So if the scenarios projected through the can initiate the Kessler syndrome, there will be much more objects in space that we need to worry about. Okay, so the question is that what do we do at the University of Arizona? I want to give you a couple of examples, right? When we started this Space Situational Awareness Arizona, we leverage on the fact that we are a premier university and a lead in astronomical observations, right? We have a lot of telescopes managed by Stewart Observatory. There are large telescopes. We're talking about somewhere between 22 and 25. However, we quickly realized that these big telescopes are usually good for surveys. An example is Catalina Sky Survey, which worries about NEOs, and we'll talk later about it. But for artificial satellites, especially the one flying in low Earth orbit or medium Earth orbit, you need small telescopes because you need to track them very, very quickly. So we started putting together some of these assets. For example, one example here is this Raptor. Raptor telescopes, which is on top of the Lunar and Planetary Lab. The interesting part about this was built as a custom design from a senior design projects at College of Engineering. It was a combination of different department students. It was a really good job. I mean, they built something like 100K telescopes for less than 10. And we're very proud of it. But those are very interesting telescopes because we can look at the Geo Belt, the geostationary orbits, right? And the innovation of this is basically that we do spectroscopy of this. So we take not only light curves, which is light reflected as a function of time, but also spectrum of this. And you see that you can, if you use the spectrum, you can basically distinguish between, or come up, you can distinguish between two different objects, right? But also, in principle, you can unmix those. And, we also have a laboratory led by Vishnu, where we combine measurements and relative transfer model to try to untangle, the different components that are made up of a spacecraft. That's one example of hardware dedicated that we have. Another one that we are just recently standing up, it's something we call the Stingray network. And the motto of this is all objects all the time. We call it persistent photometry of the Geo Belt. Basically, using some components off the shelf sensor, we were able to put basically a set of 16 cameras that can cover a field of view of about 120 degrees. And they can be constantly pointed at the sky, of course, at the night, during the night. And it turns out that if you put 6 nodes around the world, you can just basically persistently cover the Geo Belt, all the time. Now, the first node is here is funded by University of Arizona. We have partners with Italy and Australia already established that we can put an additional 2 nodes, toward the 6 necessary. This is the status of this. It's currently deployed at the Biosphere II observatory. We started, this is already online. We're just troubleshooting the few things. It's just next to this, the wonderful Bio 2. It stays in these casitas. We have a set of 6 casitas where we can also host additional Raptors type of telescope, but this is the way it looks. So basically what you do with this, you just point at the sky and continuously, get data and process the data. So the question is that now, what kind of data are you taking? Usually we come up with light curve, as I mentioned. This is basically light, how much light is reflected as a function of time during the observation. Those are called light curves. And the idea is to use these light curves to do basically classification of objects. Can we distinguish between the different objects? Now here, I show you some simulation where, first of all, the light curves depends on the size, on the shape of the objects, on the attitude state, right? But you can see that there is a difference between geosatellites with some pointing solar panels, which you see a typical response like this, and on the right side you see uncontrolled rocket bodies, they're tumble. Okay, so that tells you that light curves can be used to basically, in principle, discriminate between these objects. But how do you process all this big data, and how do you come up with algorithms that are robust, right? One of our answers is use deep learning methods, and this is also because it falls under my expertise. Yeah, I don't have to convince you that we are that deep learning, machine learning in general, have made enormous advancement this past few years. This is enabled by computing speed, massive, parallelization, GPUs, but also data availability. Now, when you point at the sky and you continuously collect data, then this becomes a big data problem that machine learning algorithms are specifically designed to deal with this kind of. So one of the algorithms that we deal with and we customize is the workhorse of deep learning, which are called convolutional neural networks. This is an example, a graphic example of a standard convolutional neural network that has been designed to deal with images. In this case, you give them the images, and the system basically learn to do higher and higher abstraction as you move from the left to the right to give you an answer about what kind of objects are you looking at. So it mimics somehow the cortex, the functioning of the cortex of the brain. In this case, we adapted these algorithms, and instead of giving the image, we give them light curves. And as we move through the network, we start to figure out different features in the light curve that can discriminate between different objects. And this is one of the things that we've been successful. We tried in simulation, we got 99%. Accuracy. On a global database, we were able to achieve about 85%, but we're still improving. So it's Air Force was really impressed by this kind of algorithm. There is a lot more that we can do. For example, we're interested in using machine learning to understand behavior of the space objects. Let me give you, here you see this spinning object. What is this? This is a deep network, it's class particular called deep autoencoders that take a bunch of light curves and then compress it in a three-dimensional space. And now you see that when you look at the three-dimensional space, you start seeing clustering of objects. So the algorithms cluster the data on itself in an unsupervised version, and each cluster represents a class of behavior of an object. So we're trying to work on these objects to understand how we can discriminate between LEO object, MEO object, GEO, 3-axis satellites, and so on. Okay. We're also interested in making a connection between a purely what we call data-driven approach with what we're using in aerospace engineering, which is first principle physics-based models. Okay. Another interesting projects that we're having, we're trying to use another deep learning framework called reinforcement learning to basically teach a telescope to observe and discriminate on its own. Okay. We basically have a system that we can train him to, for example, observe on his own the object so that you can autonomously and continuously keep custody of the objects and not lose it. That's another example of this kind of problem. David mentioned also that MPI of this FRL cooperative agreement. It's about $3.5 million that we got from the Air Force. The original project here was to build what we call a dedicated cyber infrastructure for space situational awareness. And we leverage on something that already have on campus that University of Arizona got from NSF about 120 million to build an infrastructure where people can share data, can share algorithms, process data, and so on. So we pitched this to the Air Force and we say, hey, you guys don't have any place where you can internationally really share data, test algorithms, put together algorithms together so that you can go end-to-end from data to products. And products in this case can be actionable intelligence. What it means something that can support the decision of operators that have to understand what an object in space is doing. So we went on and started building this infrastructure. The interesting part is that we're part of two projects called the Phantom Echoes 1 and 2, and we're collaborating with 5 nations. Besides Air Force, United States, we have Australia, New Zealand, England, and Canada. And we try to do this cooperative effort where basically every nation, try to track an object that observe it continuously, but there is a handover and data sharing and algorithm processing that happens through the VERSA. So VERSA plays a major role into this. I want to go on and show a little video that express what we do. In this case, we try to, the 5 nations started observing, the raising and the tracking of this object from built and launched by Northrop Grumman called Mission Extension Vehicle. Basically, this is like a jetpack that hooked to a satellite and extend the lifetime. It's like giving him more propellant. So here is a video that shows a little bit how this Phantom Echoes works. It's a couple of minutes video. So bear with me, it graphically shows the processes. This is the Northrop Grumman animation. You see, he's trying to dock with the satellites, right? And try to hook it and extend his life. So, these things took 3 months to raise to a geo orbit. So the tracking was really hard because this is low trust. And we put together some algorithms here, which is a flow of algorithms provided by different nations so that we can start, for example, uploading the data, right? This has come directly from telescopes into the VERSA database, and they start getting processed by this collaborative research environment. Here you have all the algorithms that became an app, right? And they can be tied all together in an automatic fashion. You can go end-to-end directly, alert the people about this. And the overall goal is to do astrometry, figure out from the raw images what is the right ascension and declination in the images, and then eventually do some initial orbit determination, as well as a final orbit determination when you know for sure where is the object. But since the orbit changes, you have to continuously track. So the nation do this, on a rolling sequence, getting cue from the others, and everything is enabled by this cyber infrastructure. Okay, I think kind of explain a little bit the reason. Here shows manually how this works, but we automatize it, and we're very excited about this. We also took some data. One of the most important data for which the Air Force was really impressed is also the tracking of some of these NEV objects, right? And the Intelsat satellites that was supposed to hook using the Large Binocular Telescope. Basically, Large Binocular Telescope is managed by University of Arizona. It's 2 big 8 meters dish. One is a finder, the other is a science. But we coupled this with another of our telescope, where we started giving an initial tracking to figure out where this is, then pass this information to this LBT. And what you see on the right is imaging. Now you're not looking just at the dot, what they call unresolved images. Now you resolve the image, and you can see You can see, and this is why the Air Force got really impressed, because with this 8 meters, you can image and just visually see the spacecraft. You can recognize the body with the 2 solar panels deployed. Just want to mention that our students work really hard. Here you have Tanner Campbell, one of us that did the work. So let's see. Now we move. This is a little bit of an overview of what we're doing for SSA, but we're not done, because through Vishnu especially, we have a lot of experience in planetary defense. And the planetary defense, by definition, what it means you want to defend your planet against potentially hazardous objects. And Vishnu is the lead and the coordinator for what they call the Planetary Defense campaign and NASA Planetary Defense Office. I put here a little slides that understand a little image from the planetary, or graph from the Planetary Society that shows the hazards by the numbers. You see that basically you have different categories, right? 3 meters, 30 meters, 140 meters, and 1,000 meters. It turns out that the most dangerous is 140 meters and above, and the issue is that you don't have that much of information about this. You know the big one, 1,000 meters, but greater than 140 meters in general, between 140 meters and 1,000 meters, we don't know that much, okay? So how do we do this? Well, one is Catalina Sky Survey, great survey. It's been pretty much dominant contributor of all the discovery of near-Earth asteroids and comets. Just to give you an idea, just 50% of all the new object discovery has been done basically here in Arizona, and 538 NEOs greater than 140 meters have been just discovered in 2020, just to give an idea. However, importantly, we have the upcoming NEO surveillance mission, which also will enhance the ability of finding objects greater than 140 meters. This is led by Amy Menzner at Lunar and Planetary Lab. It's about $700 million mission. Vishnu is basically the deputy or science investigation team lead. I have I lead the role in the target follow-up group. I'll tell you in a little bit what we're doing. This mission was basically is a response to a goal given by Congress to NASA. It's called the George E. Brown Survey Act, where NASA should discover greater than 90% of all NEOs larger than 140 meters by, well, I say here by 2020. That was the original one. Of course, here we're talking about now 2030. A little bit of mission objective. This is basically what it is. It's a spacecraft built by Ball Aerospace, and we build part of the instruments. We manage the whole mission. It's basically a big infrared telescope. Is sent in the L1 system between the point, which is a point between the Earth and the Sun. And basically, what you do, you survey the sky almost in an horizontal fashion, and try over the years, to get to the point greater than 90%. You need infrared detector because asteroids are extremely dark, and you can detect it only not on reflected lights, but on emission light, which depends on the temperature, and you see it in the infrared. Moving forward, just very quick, what we're doing with my group, we have basically a major goal of developing an operational intelligence system that can generate the target ranking for all the object selected, basically give it priority, and reason over the data. Okay, reason over the data means tell NEO surveyors what is the course of action, or also advise other ground systems what to do. And because we're expecting NEO surveyor to get quite a bit of data, then these things might go, an autonomous system is the best thing that you can do at this point. Just a very graphic pictures here. It shows the kind of methods that we use. We use intelligent system, couple of keywords here, fuzzy cognitive maps, Bayesian networks. What we do is basically we capture the knowledge base, the way basically a planetary science think, and in this case we try to infer, which is the priority of the objects using these methods. And what you see here is just a simulation where we use for a population of asteroids to test actually that this is okay. I think I'm running out of time here. I probably didn't take too much. SDA is an exciting field. theoretical and practical importance. We are at the University of Arizona in general and in College of Engineering at the far front research for data collection, algorithm development, data sharing, and so on. And we are also trying to use techniques from Planetary Defense, and where we play a major role in the new survey mission. And I stop here, and I think we can move to the Q&A session.
Excellent. Thank you very much, Roberto. Welcome, Vishnu. I introduced you previously, but we're really glad that you're here and just in time for the fun stuff. Roberto, I'm going to start with you. Before we really get heavily into space, you did mention that your telescopes, some of them are rated the Biosphere II. I realize the Biosphere II has activities well beyond things that you're working on. Can you just, share a little bit about this unique facility as an asset to university and community and in our education and research missions?
I mean, it's an excellent, I would say, fantastic research facility. It started as a closed system, right, to simulate the planetary ecosystem. We wanted to do, to see if, a bunch of astronauts could survive in a closed loop environment. However, over the years, in the 90s and in the beginning of the century, it turned into an earth science facility. And U of A, after Columbia University, took everything over. There are specific plans here to develop analogs for space habitats and food production. I was actually one of the lead for the NASA-funded Lunar and Mars greenhouse in collaboration with the College of with the Control Environmental Agricultural Engineering. From an SSA perspective, I showed some picture. We have a lot of space. It's ideal for non-light pollution. It's close to a research facility. They have casitas where we can organize workshop, have people stay there, and we have, of course, a direct connection with U of A, servers and so on.
Good, excellent. Thank you for that. Vishnu, I'll come to you. In the talk, Roberto presented, the concepts of spectral imaging to identify and track these objects. Is that a new concept in space, observation? And can you talk a little bit about maybe the limitations and strengths of that? And, feel free to dig into details a little bit more. Our alumni always welcome hearing about that.
Sure. Thanks, David. So I think spectroscopy itself is not necessarily a new concept. People have been using spectroscopy for more than 100 years, for astronomy especially. But applying to, space situational awareness, I think that concept is a little bit new, fundamentally because initially when people tried using spectroscopy to characterize or, categorize objects into different taxonomic types, a lot of the work was done in an operational sense without understanding the systematics. So where we come in is that we work so hard on systematics as a basic research enterprise at the university with students, is that we understand what are the limitations of the whole technique. And so we're able to better interpret and better use the technique itself for categorizing objects. I think that's where the difference comes in. And also, spectroscopy is a tool. A tool is only as effective as the person who uses it. So it depends a lot on the individual. So we focus a lot on training students on the fundamentals at the university. And so when they go out and use the tool for their careers, they know the foundation is really strong. So I think, that lends to our strength as a, education institution. And also it helps solve the age-old problem the Air Force has about how to track and characterize these objects.
Excellent, good, thank you for that. To our audience members, please feel free to submit questions into the chat. I've pre-selected a lot of questions that were submitted in advance, and we'll try to pull a few in real time, which I'm going to do right now with Roberto. So someone asked about, what are the probabilities or, risk for humans that are working in space, maybe the International Space Station, or traveling to the moon or something, being struck by a near-Earth object? How real is that? I don't need a probability, but is that a real threat, and is that something that we worry about?
There is, I would say that more than the humans working in space, I think the Geo Belt, which is more dense, is more problematic. For example, there is the Apophis, spacecraft, no space, sorry, asteroids, is coming close within a couple of hundred meters. Well, am I saying right? No, a couple of hundred kilometers with all the uncertainties you can have near the Geo Belt in 2029. That might be disruptive if there is an uncertainty that go through the belt. Vishnu might want to comment that he's probably been in the planetary defense longer, so he might say something about it. So
yeah, sure. I think Roberto is right. The fundamental threat, I think, is for large objects, just because there's more real estate. So obviously, there is monitoring of, say, meteor showers, especially to see what threat it is for the ISS. But the density is relatively low among most meteor showers. They're not like rain or a monsoon shower that we get in Tucson. So, but still, definitely there's activities in place. The threat itself is from artificial debris, to big things like the ISS and human life in orbit, than natural hazards as such, I would say.
And our lumber, we're just going to stay on this thread for a second because our lumber are interested in the physics. So I think I'm going to interpret this question. If you have two objects in the exact same orbit, do they always necessarily have the same speed, or can they have different relative speeds to each other?
Depends if they are in the same, if they are one after another. Yeah, of course they change. It depends how big is the separation, right? Remember that, from the famous, you can apply Newton's law, but you can also apply the famous Kepler's, the 3 Kepler's law. You have an ellipse, right?
Right.
When you fly around a primary body like Earth.
Right.
Of course, what happens is that the velocity, the only way the velocity is constant is if the velocity is if the orbit is circular. It's an ellipse. You will have change of velocity continuously, even if they are exactly in the same orbit. By the way, it never happens that they are in exactly the same orbits. Plus, there are perturbation. So the relative motion becomes extremely important.
Excellent. Good. I'm going to stick with you, Roberto.
Yep.
We hear a lot about big data and artificial intelligence, machine learning. You touched on it in your talk, but what are the advances that have been made within the realm of space situational awareness? And is this something that the College of Engineering or LPL is investing in with regard to new faculty?
All right. So basically, I would say, first of all, as I mentioned to you, AI is extremely important. There is a lot of interest. The problem is that a lot of people coming from my community do not have the tools. Some are very unique in this regard, because that happened when I was doing my PhD with my former advisor, Barry Ganapul. We started looking at neural networks, and it's been 20 years experience. Now there's a lot of interest. However, we are the only one really that actively do research on this area. There are a few other here and there, people trying to do it, but I can see that they're not very systematic. So it's extremely important also because I know that, in system engineering, for example, SIE, we're hiring people in machine learning. We are hiring also at AME in robotic and machine learning. So those are all expertise that needs to be put forward, because there is a lot of potential, but we are just at the very beginning. And, one of the reasons for us to put the Stingray network was really to collect a large amount of data where we can seriously deploy deep learning algorithms because they work on big data. And that's one of the things. So I think we are at the forefront for this. And by the way, I'm the only one, I'm pretty much teaching the only deep learning course on short course at the Amos conference, which is the most important conference for SSA in the world.
Wow. That's great. I'm glad that we're leading in those areas.
Yeah.
Vishnu, I'm going to kind of expand space a little bit to inquiries I often get, which relates to space mining, especially given University of Arizona's deep history in space and history in mining, as they come together. Can you give any thoughts or, perspectives on space mining, and you can tie it to space situational awareness? Does this introduce additional components? People talk about assembling things in space in an already crowded area. You want to give us some thoughts on that?
Yeah, absolutely, David. I think the biggest users of anything we mine in space will be things in space. Rather than trying to bring stuff back to the Earth. The immediate need is obviously the most valuable thing is not precious metal like gold, platinum, but it's water. And primarily the argument being made is that water can be split into oxygen and hydrogen. You can use it as fuel and oxidizer. So Roberto talked about the Northrop Grumman mission to refuel and put a fuel pod on defunct geostationary satellites that can no longer do station keeping, but are otherwise perfectly functional. So if you can go pump fuel into it. So right now we're sending fuel up in rockets to dock. The in future at some point, it might be that those fuels will be derived from things like water-rich asteroids. But the challenge always has been the market, right? There have been brief spurts of investments throughout the last 20, 30 years in asteroid mining. There's the period with a lot of activity, a lot of companies come up. And again, like I said, there's no longevity of those industries. But what we are doing at UOA is primarily focused on, everybody talks about water. Is it really water that you can drink? Is it like a, bottled water or stuff that comes off your tap? What else is there in it? So in my lab, which what we do is we heat up these water-rich meteorites to extremely high temperatures and see what comes off it. And try and analyze those elements that come off it to try and see what are the contaminants. We know there's water, but what else is there that we don't want to be there, right? So that's the basic research area we're focusing on. As far as the traditional challenge of having too many things in space and how that affects, some things like space traffic management, I think the more immediate future in the next 5 years, we have to worry about mega constellations, not just in terms of debris generation, but also ground-based astronomy. So I think that's where the concern is rather than space mining, I would say.
And I'm going to just pull up again in real time because you guys are doing great on the questions. Do you see any kind of a consensus among nations to limit allocations of how many things you can put up, especially private companies? Hey, you can put up 20 small sats a year or a month. What do you see down that pipe? And I'm tapping in a little bit to your policy part of your PhD, but do you see limitations coming? Will we get together on that?
I mean, at some point, as we all know, we are human beings as a species are reactive than proactive. So unless something bad happens, right, we're not going to, do a whole lot. So there is actually this thing called the Kessler syndrome, where, the number of objects in low Earth orbit is so high that every debris generating event will cause for a cascading scenario where you would have essentially a debris cloud around the entire Earth. You cannot send a spacecraft, say, to Geo, unless you heavily shield it, which limits down the useful mass of the satellite and the lifetime of that satellite again. So, that's a real threat, and I think a lot of private companies are trying to get their stuff in space so that they would be potentially grandfathered in case a regulation shows up at some point. But as of now, it is pretty crazy, So I have a undergrad student from AME. She's actually studying the brightness of the Starlink satellites to see, how does that affect ground-based astronomy. She's an engineering undergrad student. So her father works in SSA, and he was very interested in, working with us. And so Grace came as a freshman, and she's been working. She's going to graduate next year, go to grad school. But, her main project is looking at, are these Starlink satellites, so bright that they would affect astronomical research, right. So we have students working on that too.
As I kind of said in my opening, it is a bit of the new Wild West, right? Up in space. Oh, yeah. Let's kind of, you mentioned students, so let's kind of loop back to education just for a minute. I'll ask you each to comment on kind of your professional, life to get you to this point, and share that, how do you share that with engineering students on, if you want to work in space, what are the paths you can get there? And Vishnu in particular, you had an interesting path, right? You started off not necessarily as an engineer, but look at you leading big missions. So I think that's inspiring to others that might want to pivot. So I'm going to go with Roberto and then to Vishnu.
Well, I think there are a few ingredients that needs to go together. Curiosity, driven, passion, but important, and this is to me, I can stress this, is application and consistent application to build strong fundamentals, because you don't know where your career is going to be. My degree in Rome, I was interested in space, of course, but it was on aeronautical engineering. And when I started here, I had no idea about neural networks. And then I became eventually an expert on this. But how did I do it? From, this is a typical computer science / even electrical engineering. Because I had strong fundamentals, but something that I cultivated over years. So you can react to an emerging fields. For example, another one is hypersonic. Hypersonic, we're working to intelligent system to guidance control and navigation of hypersonic objects. And this is something that is recently back. And the reason I was able to quickly react to this is because of the background. The key three principles I like to suggest is what I call aspiration, inspiration, perspiration. You need and perspiration is extremely important because you need about 10,000 hours of work to become an expert, to master a field. And I have to say, and these are general critics, to the overall global, I don't know if it's global, but at least Western world new generation, they're lacking this idea of, they want everything, now. And I think we have to understand that in science is a building blocks. And my strong suggestion that I do to the advisor, to advise my students is like, Rome was not built in a day, so.
I think that's great advice. And I also iterate to students all the time, get your fundamentals and then take that where you want to go. Vishnu, do you want to kind of share a little of your journey here?
Oh, sure. Yeah, no. So like I said, I grew up in rural India without power for most of my early childhood. So I got into astronomy because I had nothing else to do once the sun went down. So that's how I got inspired to get into astronomy. And I did it as a hobby for the longest time. Obviously, I didn't, necessarily go into the sciences right away. So I went into art. I went into, what other thing India is known for apart from science is Bollywood. So I made movies in Bollywood for several years, and I got tired of it, and I went and ran a newspaper for several years. So, I had two completely different careers before I decided. I mean, the important thing is, in everything is you're in search of truth, and you use some medium to communicate it, to bring about change. You know what I mean? So that seems to be a common theme across, everything I've done so far. I wrote a lot as a journalist. I write a lot more as a scientist, just the nature of things. So like Roberto said, focusing on skills rather than knowledge, and focusing on the skills that are transferable, not just in a single, job or something like that, but across many careers you would want to take. It helps a lot, be it writing good English, being good at programming or math or even presenting. So, I, do not, directly go and recruit students. I usually get them. They come to my office and they say, I want to work with you. And we just go from there. And it's worked out wonderfully. I mean, that's one of the most, a rewarding aspect of my job is to, have a brief interaction about 4 to 5 years with these students in the prime of their life. Really, amazing feeling to work with our students.
Absolutely. That's great. And again, you're a great example of different perspectives to problems, right? I'm sure your training has helped you, right? To understand and visualize and present this data. Roberto, as you look at near Earth observations and the upcoming, NEO satellite missions, what are the most up-to-date technologies? What's on this near cutting edge horizon that you'd like to put into those instruments?
Well, okay, so for NEOs is a no-brainer. I discussed earlier, it's space-based infrared. Okay, you need to improve those. I mean, that's the way you do it. For LEO debris, there are a couple of ways of doing. There is the phase array radar type of technology. There are, for example, LEO Labs, and now the upcoming LEO Labs is a company, by the way. In the upcoming, they already stood up Space Fence. They're all radar or phase array radars that can track debris. And of course, then there is the space surveillance telescopes for geo debris. There is one that just put it as part of what they called satellite space surveillance network. In Australia, it's a 3.5 telescope that covers the gap. But on the horizon, I would like to point that spectroscopy, spectral curve is really an untapped field. Again, I mean, Vishnu mentioned it to this. We do spectroscopy, and in general, spectral images, analysis of object of images taken from space looking down. But we don't do the opposite. And I was shocked. About three years ago, we started a conversation about this, and we were shocked that people were dismissing on the idea, but also there were no fundamental research done on this. So we need to start from scratch. But we're proving, especially through the observation that Vishnu is doing, and I'm mixing algorithms that are derived from artificial intelligence, that we can really discriminate through this. There's a lot of potential. And also, the other important thing is, in general, data management, data processing, and decision making, because there is nothing, it's a big data problem. How do you manage? How do you give actionable actionable intelligence for the operators to understand behavior of satellites?
Good. Wow, that's great. So Vishnu, when you look at the space situational awareness, opportunities for engineering solutions moving forward, in particular, again, I'm going to pull a question right out of the Q&A, particularly focus on ways to mitigate, space debris, collect it. Are there credible ideas out there to gather? I know it's a hugely daunting problem. We can't get plastic from the ocean, which is right here in our backyard. So when you talk about rounding up debris in space, what's out there? What are some ideas?
Yeah, I think just like trash on Earth, right? Trash in space starts with self governance and having some guidelines, at least to have safe disposal of objects. The Europeans are doing a slightly better job at it than us. But at the same time, things are done better in geo, because we know that if you put something in geostationary orbit, even if it's a derelict satellite, it's going to stay there for a long time. And those orbital assets are very, very precious to us. They don't come easily. And so there is a relatively, I would say, loosely coordinated geodisposal guideline that people mostly follow. But it's a challenging thing. If you're a satellite operator, you're a business owner, essentially, and let's say your satellite is sputtering, you're running on fumes. You have to make a decision whether, I do the right thing of moving it into a graveyard orbit, or whether I can eke out another 2-3 months of operation so I can make a little bit more money. So it's a challenging thing. So there has to be incentives for business also for good behavior, right?
Yep.
If you take the hit and you do the right thing, there has to be some incentive, either in terms of lowering their insurance premiums going forward, something has to, be there to incentivize businesses for good behavior. I think, it has to go both ways, just not saying that, it's a purely an environmental, aspect, because, as humans, like we are reactive, we're also greedy, right? So you have to appeal to, our human nature, so to speak, to fix the issue. But as far as active mitigation stuff, the sun is a big helper. We're going to go up into a solar maximum. So that's going to have the atmosphere expand because of the heat, and creates more drag, and a lot of stuff from low Earth orbit is going to come down. Some things we don't want to come down, things like the Hubble Space Telescope, which has survived beyond its life cycle, because the sun has been extremely quiet the last 5-10 years. But again, filtering out debris, definitely that's the case. We see a lot of the Starlink satellites also deorbiting, so that like, for example, naturally decaying. But you have to be really careful. I mean, there's stuff still out there at about 1,000 to 2,000 kilometer orbits that's there from the Cold War,
Right.
And we track that stuff, and it's never going to come down, and it's scary, So unfortunately, there's no one clear answer as to how we go about pulling everything down.
Good. Roberto, I'm pulling one from the pre-submitted questions. We talk a lot about codes and standards in engineering and senior design. What international, government, commercial standards, guide your research as you start to do some of these space issues and as you collaborate, internationally?
Well, that's a system engineering kind of questions. What I realize that everybody has his own culture, right? Both nationally and international, especially if you go across nation, and things gets complicated. But even nationally, my experience, for example, we interacting with Goddard, Lockheed Martin, Kinetics. The struggle was not the principles, the struggle were the system process that was in place. And whenever you have to put everything together, it's very complicated. So we have to learn. What I did, I spent quite a bit of time on learning about each other and try to smooth things out. And so this is in general true for all sort of research or applied. At the university, we're more free spirits. We tend to go in all sort of directions. But when you move from basic to applied, things needs to be streamlined in a certain way. So I think it's extremely important to learn about the system process from others. That's what I did.
Good. Vishnu, again, our alumni are interested in policy type issues, and you did part of that for your PhD. So, in science and technology, the question is oftentimes, these domain first movers can help set precedents and set up standards. What kind of opportunities or even conflicts are out there for space situational awareness, again, on this kind of policy front?
Yeah, absolutely. So like, for example, Starlinks, right? That's the largest mega constellation that we have right now. Their reaction to, say, the astronomical community, right? You know what I mean? So when the first Starlinks went by, it's like watching Santa Claus, go across the sky, because they're like, lights, reflected off basically these satellites, because they're aluminum chassis, because they're building on the cheap, and they're just reflecting off light of this aluminum, right? So when the astronomical community came to, for example, SpaceX, and said like, hey, this is going to cause a problem to us, they listened, and they made modifications, and, so they changed the orientation of the spacecraft in such a way that, yes, in the initial orbit, when they're just launched, they're going to be bright, but in their final orbits, they should, be in a certain orientation. In other words, it's a company that is reacting to a community that is being affected by it without the government even being present as a mediator. You know what I mean? So things like that, because, like I said, a lot of companies today are very socially conscious about the image and the perception of it, and they want to maintain and be, a good player in being part of the solution rather than being a part of a problem. So not only do they want to give, global internet to, places that cannot get broadband internet, but also they want to be, somewhat receptive to the astronomical community. Now, are they going to solve all the problems that are going to affect the astronomical community? Probably not. It's still going to affect, and that's where academia comes into play, into trying and quantifying those effects, and, going through the peer review process. So it's not anecdotal between the community and the company, but there's some scientific rigor. And that's where our students are coming to play, studying these satellites and mega constellations.
Excellent. Good. We have time.
David, just want to add real quickly. Reality is that if a nation put a spacecraft in orbit, okay, there's no regulation that can tell them what to do and how to operate. Actually, many times they might do something just out of inexperience, and and they might not share the data, and we don't know. Nobody knows what the system is doing there and causing damages. There's no law to enforce it at this point.
Very interesting. Roberto, we have about 2 minutes, and I'm going to give you the last question. You were involved in the OSIRIS-REx asteroid sample return mission, noting that it successfully collected the sample on October 20th last year. So I'd be remiss if I didn't ask you what's in store for OSIRIS-REx now that that sample is safely on board, but it's still far from Earth.
Okay, as you know, the sample will be returned 2023. It turns out that there's quite a bit of propellant, so that for a phase F extended mission. So the current proposal, from what I understand, is going to the Apophis asteroids, okay, which is the one that I mentioned earlier. It's going to come close proximity 2029, very near to the Geo Belt, and it's important because this thing is 370 meters, and there is a possibility of impact 2026. 68 is estimated 1 over 150,000 cases. But so that's my understanding, is that it's not a done deal yet. There is a proposal, but there's a lot of interest from the community to just redirect the spacecraft toward Apophis.
Fantastic. All right. Hey, I think we've come to the top of the hour. This went really quick today. Some really good stuff, some great questions from our alumni. And I just want to thank everyone and our friends for joining us. I want to wish everybody a good day and hope to see many of you back next Wednesday for our last installment around additive and advanced manufacturing. Wish everybody a great day. Thanks for coming, and see you next time.